Hey, welcome back everyone. So in this video, we're going to cover the Poisson distribution and how to apply it to decision-making situations. So we won't be spending time on the hypergeometric distribution in class, but I will briefly discuss it in this video since it's something that I have used in practice in one of my previous jobs. So let's get started. The Poisson distribution is where we want to figure out the probability of something occurring over a space-time or a well-defined segment or interval or unit of inspection. A good example to help remember the Poisson distribution, since it can be kind of funny to say, is to think about potholes on a city street. We could use this distribution to determine the probability of hitting a certain number of potholes as we drive along the street. So think P for Poisson or potholes. So here is the symbol lambda, and this is the average number of successes or outcomes of interest in our one segment. So using the pothole example, perhaps the average number of potholes is 3 in a city street. Now with the Poisson distribution, the outcomes of interest are random because we're working with a discrete random variable and they are countable. So you can count how many potholes are on a city street. Now the probability that an outcome of interest occurs in a particular segment is the same for all segments. So when we're talking about how many segments we're studying, we'll denote that by the letter T. It's important that you remember that the two symbols that we'll be using are lambda and T for the number of segments. So let's look at some examples. So let's say we wanted to know the number of patients who arrived at a hospital emergency room per hour. We could use the Poisson distribution to determine the probability of a certain number of patients that will arrive. This could help with staff planning for doctors, nurses, and staff members to support the incoming patients. We can also apply the Poisson distribution to the number of calls a Dell tech support group receives in a 30-minute period. So in this example, the segment is 30 minutes, whereas in the hospital example, the segment was per hour. So it's important to know that the probability of calls received in a particular 30-minute period so that we could staff accordingly, just like in the hospital example. So another example will be the number of cars served at a gas station in a 24-hour period. So in this example, our segment is 24 hours. The segment can be anything really, but we have to identify it in the story. So in this example, it might be useful to know how many pumps we need at the available gas station, staffing again, or how much gas do we need to have on hand. So another instance is the number of defects per square meter of leather. So if we think about raw material like leather, we can estimate the probability of defects that you're going to see on the raw material. So here are the related formulas that you'll need to be working with for the Poisson distribution. So by now, you might be noticing a pattern where we're learning how to calculate the mean or expected value and standard deviation for every kind of distribution. We also need to calculate the probability of X for each distribution. So let's break down all the variables in our different formulas here. So again, we've got our lambda, which is our expected number or the average number of successes in one segment. So T is the number of segments that we're interested in studying. So if we use that pothole example again, our expected number of potholes on one street is 3, and say we want to study 5 city blocks, so we'll just take 3 times 5, meaning when I drive up and down my 5 city blocks, I should expect to see approximately 15 total potholes on an average number of 3 potholes per street. So with the standard deviation, we're going to simply take the square root of our lambda times T. Then for our probability distribution here, we have lambda times T raised to the X power. So the X is the number of successes in T segments. So remember, anytime you got P with parentheses, that's the probability of some event. The E here that you see in the formula is the base of a natural logarithm, and its value is 2.71828. So you won't be expected to remember that. You can use your calculator, and if you look for the button with an E, if you try it and press the E button, you should see 2.71828 with a bunch of floating decimal places to the right. So now, if your calculator does not have the E button, then you will have to manually type in the number when you're doing the formula. Now, our natural log that we're using with E is also the exponent in this case. So you'll notice it's a negative lambda times T. You will take the lambda T value and just make it negative and then use that as an exponent. When we multiply this across, we'll divide it by the x factorial. So if you recall from the last video, factorial is when you multiply the number by every number below it down to 1. So again, factorial of 4 is 4 times 3 times 2 times 1. Again, if you have a calculator with the factorial button, this will do it for you, so you don't have to do it manually. Here's an example of a distribution for the number of arrivals to a checkout section of your favorite store per hour. So here our segment is 1 hour, so we're only looking at one segment, so our T is 1. We are given our average number of arrivals is 16 per hour, so you can see based on our distribution here, 16, which is my average in an hour, will be somewhere in the middle. So when we look at the other possible number of customers in our distribution, the probability is illustrated by the height of the bar. So for instance, if we wanted to know the probability of 26 customers arriving in an hour, we can see that the probability is very low compared to, let's say, 16, because 16 is our average. Here's the actual calculation if we wanted to know the likelihood of 12 people coming to the checkout stand in 1 hour. We could plug in our numbers into the formula where x equals 12, and you can see here on our probability distribution of 12 customers is 0.0661. So the shape of the Poisson distribution depends on the lambda and the t combined. So you can see here when we multiply lambda and t together and the product is 0.5, our distribution looks different than, let's say, when our lambda t is 3. So let's look at the steps to find the Poisson distribution. So first, we define the segment units that we're looking for, whether it's time, space, or volume. Then in step 2, we'll find our lambda, which is our mean for our random variable. In step 3, we need to determine our t, which is our segments that we've identified in step 1, and then we'll calculate by taking lambda multiplied by t. Then in step 4, we want to make sure we understand the problem and define the event of interest that we're going to solve for, and then we're going to use the Poisson formula or Excel to find the probability. So the Poisson function in Excel consists of 3 fields. We have the x, which is our expected number of events, the mean, which is lambda multiplied by t, and then whether we want to return the cumulative probability. So this is like what we've seen before in our other distributions, where if it's true, that means our distribution is cumulative. That means it reads from the left to the right of the curve. If we input false, that means we're looking for the probability of exactly a particular number of events. So let's look at problem 5.51 in the textbook. So arrivals to a bank ATM followed the Poisson distribution with a mean equal to 3 customers per 15 minutes. What is the probability that in each 15-minute segment, 1 customer will arrive at the ATM? So first, we need to identify what is our segment unit. So this is defined in our story. So in this case, it's every 15 minutes. The mean or lambda was given in the story as 3 arrivals. And then specifically in each 15-minute segment, so there's only 1 segment. So we must find our lambda times t. So I'm going to take my lambda of 3 times t of 1, and that gives me a lambda t of 3. So this is the mean that we're going to use in Excel. So you might be thinking to yourself, that's kind of confusing because we have a mean in our story, which is our lambda, but we also have our lambda times t, which is the mean used for Excel. So our event of interest here is the probability that x equals 1 or 1 customer comes to the ATM. So we're going to use Excel here. So here are the function inputs. We'll plug in 1 for x, 3 for the mean, and false for cumulative since we're looking for an exact probability value. And we get 0.1493. So let's go ahead and do B for the same story. What's the probability that fewer than 4 customers will arrive in a 30-minute segment? So looking at the problem closely, we can see that our segment unit remains 15 minutes and the mean or lambda given in the story is 3 customers. So I've plugged in those values already. In part A, the number of segments was 1 because we were looking at the number of customers to arrive in 15 minutes, which is the same as our segment unit. But here, we're looking at a 30-minute segment. So our T is going to be 2 segments because there are 2 15-minute segments in 30 minutes. Now, for our lambda T, we're going to take our lambda of 3 arrivals and multiply it by our 2 segments, and we get 6 for our lambda T. So our event of interest is the probability that X is less than or equal to 3 or fewer than 4 customers come to the ATM. So we're going to go ahead and use Excel again here. So here are the function inputs. We will plug in 3 for X, 6 for the mean, and true for the cumulative. Since we now want to return the cumulative probabilities up to 3, and we get 0.1512. So as mentioned at the start of the video, we won't be covering the hypergeometric distribution in class. However, since it's covered in the textbook and I have used this distribution in practice, I wanted to at least go through some of the key points. The hypergeometric distribution is formed by the ratio of the number of ways an event of interest can occur over the total number of ways any event can occur. So the key point here is when where sampling is done without replacement from a finite population, the binomial distribution could produce inaccurate probabilities. So we're going to denote our sample as the n trials from a finite population of big N. The trials are dependent, and when we take a sample without replacement, meaning it's not available to be selected again, the probabilities change after every trial. So ultimately, with the hypergeometric distribution, we are concerned with finding the probability of X successes in the sample where there are X successes in the population. So like the Poisson distribution, identifying our success in the trial is very important with this distribution as well. Well, that wraps up this video on the Poisson distribution and the hypergeometric distribution, and that also wraps up Chapter 5.